So it helps if I record. So a prism is a very basic shape in which the base has an area and then the height perpendicular to the base. That if you cut it along the height, which is perpendicular to the height being perpendicular to the base, and the area which you cut it is parallel to the base, that no matter where you cut it along its shape, it's going to have the same cross-sectional area. So a cylinder is a very specialized prism. It's a prism in which my base is a circle. So the area of a circle, or the volume of a cylinder, is the area of the base multiplied by the height of the cylinder. In particular, the area of the base, because it is a cylinder, is going to be the formula for a circle. So it's pi r squared, and then you multiply it by the height of whatever your cylinder is. Now, most of the time, we will not be finding cylinders because that's not interesting. There's no reason to use calculus to find the volume of a cylinder. But we're going to take that idea, which is we're going to be taking slices along parallel to the base and perpendicular to the height. And we're going to be taking these individual slices and we're just going to keep slicing them and slicing them. And that way we can do shapes that are not necessarily the same. So as an example, here is this shape, and it is not a prism, and it's certainly not a cylinder. This particular shape, as you see, that the base size changes. The shape doesn't, but the size changes as you go along the height. So when you start taking the slices out of it, that this cross-sectional area at this point is going to be larger than this point, and then also at this point. So just like we did before, when we were integrating, we were finding the area underneath the curve, and we said, okay, well, what happens if this height, what is the area of this particular rectangle? And then if you remember from Riemann sums, we then said, okay, let's make, and so instead of doing two cuts, two shapes, two rectangles, when we were doing the area of the area underneath the curve, we then did an infinite number, and we found the area underneath that curve by doing the infinite number, doing the Riemann sum, and taking the limit. So what that means for us is if we are trying to find the volume by integrating, then we just think of this as we are taking all these small little cross-sectional areas. When you're trying to determine the volume, it's really a good idea to try to draw the shape and then think about the way it is being revolved. Is it being revolved around the x-axis? Is it being revolved around the y-axis? This section and the next section is we're going to give you the tools that you need to find the volume, and we're going to explore different ways of finding the volume. And then toward the end of the next section, you all get to make the choice on how you find the volume, whether you do it with the slicing, also known the disc method, or whether or not you do it by the shell method. So that's what we'll be doing in the next section. So once we have determined what the shape is going to be, then we're going to want to determine the formula for the area of the cross section. So it is the area of the cross section. Then we're going to integrate the area formula over whatever interval that we want. So let's first start out with drawing an outline of the solid, finding the volume by the slicing method. So the base is the region underneath the parabola of y equals 1 minus x squared in the first quadrant. Slices perpendicular to the xy plane are squares. So we are trying to figure out what this looks like. So the parabola is 1 minus x squared. So it's going to look something like this. So here's 1 minus x squared. Here is y, and here is x. The slices that we're going to take are going to be perpendicular to the plane. So let's see if I can draw this very well in the where this is z, and I will make this as x and this as y. So in 3 space, the volume that we're looking at is this volume, this shape here, like this. So it's saying that as I do this cutting, that my shapes are going to be like this. So if I were to look on this particular shape from the side in 3 space, this is z, this is x, and y is coming toward me, it's going to have some kind of shape that looks like that. So what I'm slicing is I'm slicing along here. Okay, so in 3 space, it's kind of like a, I don't know, it's hard to describe. It's kind of like a hemisphere type thing. I should go to geoalgebra. I should have done that. Okay. Anyways, so if I'm trying to figure out what my volume is I have to figure out what those squares are going to be. So I have to figure out what the squares are going to be so I can integrate across that square. So it's telling me that each one of these has a square base. So I have this shape, which would be one of these slices. And when I'm doing one of these slices, my area, because remember I'm just going to use this formula here, which is I'm going to integrate the area from A to B dx. So my area is, I got to figure out what this is in terms of the area. So what is the area of this? Let me give it a pause. So what we do is we think about, we're going to revolve initially around the x-axis. So here's my curve right here. I have this particular curve and I want to find the volume of that shape. So I draw my curve on the xy plane, and then I'm going to revolve it around the correct axes or line. In this particular case, I want to revolve it around the x-axis. So once I revolve this around the x-axis, I end up with this like funnel shape. So it's, if I were to slice this along that funnel shape is going to be a circle. So along there, because of the way it's being revolved, it's going to be a circle. And so to find the disk method, also known as the slicing method, is we just determine where we want to revolve, around the x-axis or the y-axis. And then we think about what the shape is going to be when we revolve it, as we cut it. So in particular, if I have this f of x equals x minus 1, so this is f of x is equal to x minus 1, the quantity squared plus 1, then here's my graph. If I revolve it around the x-axis, then I'm going to get all of these disk shapes that are there, and then I'm going to eventually get this, like, I don't know, looks almost like a weird funnel. Anyways, so what we do is we determine which way we're going to revolve, around the x-axis, y-axis, or a line, not the x and y-axis. And then we integrate. Because all the cross-sectional areas are circles, we end up multiplying our cross-sectional area by pi. So using the disk or slicing method, you're going to see it called both, the disk or slicing method, then what you're going to do is you're going to do the area, which happens to be a circle, which happens to be r. So what that is pi r squared, where r is your function. R is the height at any given time. Let me go back and show you. So this would be one of the r's that's given. Here would be another r that's given. So your radius is going to be your output for that at any given time. So your radius of this circle here, or even this circle here, is going to be the distance from the x-axis to the function. So in other words, your radius is the y value, but the y value is just the function. So with the disk or with a slicing method, depends on what you call it, your r happens to be your output, which is also the function. So when you're finding the volume rotated around the y or the x-axis, then it is simply just going to be your pi multiplied by your function squared, integrating from a to b. If you are revolving around the y-axis, then the only thing that happens when you revolve around the y-axis is that you now are going to have c to d, which are y values. Your function is going to be respect to y, and you're going to integrate with respect to y. So if they're telling me which axis to go around, then I'm going to go around that particular axis, and I'm going to use either the y's or the x's. So here are 3 examples. Which one of these 3 would you like me to do? Which one of these 3 would you like me to do? A? Okay. So what I want to do is I want to do a quick sketch of what the area is and then how I'm going to revolve it. So for this particular one, for A, I am asked to find the area between 2x squared. So here's what 2x squared looks like, give or take. So there's 2x squared. And I'm going to be bound between y equals 0 and x equals 0, so right there. And I'm going to end at 4. So my shape is going to also be revolved around the y or the x-axis. So in other words, my shape is going to look something like this. It's going to have this shape that looks like this. So it's almost like a trumpet. So using my formula, I'm going to integrate between, and they're telling me to start at 0 and end at 4. It is going to be pi, my function 2x, the quantity squared, because that's my radius at any given point, dx. So then all I have to do is integrate this, and so I'm going to pull the pi out, and I'm going to pull the, I'll leave it in there, so 0 to 4, and then I'm going to square the 2, don't forget to square the 2 and square the x, and so it's going to be 4x squared, or that should be squared to begin with, so that'd be 4x to the 4th, dx, and now I'm just going to integrate. So this is going to be equal to 4 over 5 x to the 5th, don't forget that pi, so I'll squeeze pi in there, evaluated between 0 and 4. So this is going to equal to 4/5 pi, and then I have 4 raised to the 5th minus 4/5 pi, and then 0 raised to the 5th. And so my final answer is going to be, getting my calculator out is what my final answer is going to be. And I'm going to have 4 raised to the 5 times another 4, so in other words 4 to the 6th, and then divide that answer by 5. And so I get 819.2 multiplied by pi. How was that? What kind of questions do you have for me? Any questions at all? All right, if there's no questions, I'm going to put this on pause. I'm going to scroll out a little bit, and I want you to do B and C, please. B and C. Is it awesome? So I know from y equals the square root of 4 minus x squared that when I went and solved for x, then I know that I'm going to take the positive region of it, so I don't have to worry about the plus and minus. So I'm just going to take the positive because I had to choose the positive here in my original function before I solved for the for x. So I have that. Now they're telling me that I am going to restrict it between y equals 0. So what that means for me, from y equals 0, so I'm going to restrict it from here. And I'm going to restrict it also in for x is equal to 0. So the region I'm going to be integrating is just this region. And when I revolve it around the y-axis, then when I go in this direction, then what'll end up happening is I'll end up having that full semicircle. So I'm going to have a semicircle on this one. So when I go to integrate this with respect to my y-axis, because that's what they're asking me to do, is rotate it around the y-axis, that I'm going to start at 0 and I'm going to end at 2. Because remember, this is a circle. So my integration for my y is going to start at 0 and end at 2. It is going to be pi multiplied by my function in terms of x. So this is going to be 4 minus y squared, the square root of that. And actually, let me write it this way. Let me write it as a square root and then squaring it. So 4, and then it's going to be the square root, because that's my function with respect to y, and then I square it, dy. So dy. So when I square my square root, what will happen is this is going to go from 0 to 2. I'm going to pull the pi out because it's just a multiplier. When I square the square root, I'm going to just get 4 minus y squared dy. Okay? So now I can do an easy integration here. And my easy integration is going to be pi 4y minus y cubed divided by 3 evaluated between 0 and 2. So this is going to be equal to pi 4 times 2 minus 2 to the third divided by 3 minus pi times 0. So we like that part. So we end up with, I don't know, get my calculator out. So I get 8 minus 8 divided by 3 times pi. So my exact answer is 16/3 pi, or approximately equal to, if I multiply that by pi, I'm going to get approximately equal to 16.75516. When you are putting these into WebWork, I would suggest that you use the exact values versus the approximation if you can. If you do the decimal approximation, make sure you run out to 4 or 5 decimal places. Now, is there any questions on that one before we go back and do the other one? Any questions on that one? Okay, so let's take a look at our other one. So I'm going to erase this because I'm going to need this space. And we're going to go take a look at B here. Now B is already in terms of y. It already has x equals. So what this graph looks like is it's going to be the secant, but your secant function is going to be drawn on the y-axis instead of the x-axis. So the secant is the reciprocal of cosine. So if I were to draw the cosine on the x or on the y-axis, I actually have to move the graph or my paper, or in this case my iPad, sideways so I can draw it. So this is going to look like this. That's the cosine wave. Now I don't want the cosine wave. What I really want is the secant. So the secant is what I want in the blue. That's what I want. Now remember, this is in respect to the y-axis, so your secant wave is going to be like that. Now, they want the secant wave from y equals 0, so when I'm doing my integration, it goes from y equals 0, so that's going to start at that point, and it's going to end at y equals pi over 4, so somewhere about right here. So this is pi over 4. Okay, so the shape I'm going to do is actually this shape right here, and it is going to have also the restriction at y equals 0. So this is the shape right here, this kind of like, just like a little small piece, and it's going to be it's going to be revolving around the y-axis. So that's what the shape's going to look like, the shaded region there. It's kind of basically, it's going to make like a ring. You're going to make like this donut. So when you go out, it's going to have this like donut shape. It's when you make this, the volume. Where when I pull a slice right here, it's going to have like that shape right there. So that's what it's going to look like as you revolve it around there. So I'm going to integrate this between 0 and pi fourths, because they're telling me that's where I'm going to integrate for. Then I know it's going to be pi, and then it's going to be my function. So this is going to be secant of y, and don't forget my function gets squared, because that's the radius in any given point, dy. So then this is equal to, I'm going to pull the pi out, 0 to pi over 4, of secant squared y dy. So what is the antiderivative of secant squared? What is the antiderivative of secant squared? Tangent. So this is going to equal to pi the tangent of y evaluated between 0 and pi over 4. So this is going to be equal to pi, the tangent of pi over 4, minus pi times the tangent of 0. The tangent of pi over 4 is just 1, so this is just going to be pi. The tangent of 0 is 0, so it is minus 0, so my answer is just pi. How was that? Was that okay, or is that still kind of sucky? Is that okay, or better? Somewhat better? Thinking about it being better? Are you all still alive and awake? Still a bit confusing. Okay, let's do some more examples then. So for this one, I'm going to do around the y-axis or the x-axis. The first thing I always do is I like to draw a picture, a real quick sketch. So this is the reciprocal function, and so it's going to look like this. That's what the reciprocal function looks like. Of course, it's not going to actually touch that, so let me draw this a little bit better. So this is my reciprocal function. That's what it looks like. Where I'm going to integrate from is between 2 and 3, and I'm going to rotate along the x-axis. I'm going to do a rotation around the x-axis. And so what I'm going to have is I'm going to have this shape that looks like this, like that. So it looks something like that. And so for this integration, this one's actually pretty straightforward. It's going to be the integration from 2 to 3. And I'm going to integrate pi, don't forget pi. Then it's going to be my function, which is 1 over x, the quantity squared, dx. So this is simply going to be pi from 2 to 3. I'll write this as x raised to the negative 2 dx. Now I'm going to just do my regular integration. And so I do my regular integration, I'm going to get pi. I'm going to get x raised to the negative 1 divided by negative 1, adding a power and dividing by that, evaluated between 2 and 3. So this is going to be equal to pi, I'm just going to leave that out there, negative 1/3 minus a negative 1/2 So my final answer is going to be pi over 6. How was that? Oh, yeah, look at that. I totally ignored from y equals 3. Wow. Let's just, for sake of argument, let's write that as x, and then I'll show you how to actually do the other part. Thank you for catching that. So for right now, this is how it would be if it's from x is equal to 2 to 3. So let's actually adjust for when y is equal to 3 because it's going to change it. So had that been y is equal to 3 and x is equal to 2, then I'd have to figure out what the x is that produces this y. Thank you for catching that. I just totally read that as x is equal to 3. So I have to figure out what the y value or the x value that is associated with that. So I'd say 3 is equal to 1 over x. And so solving for x is equal to 1/3. What that means for me is when I go to do the integration correctly, I would have had 1/3 here and I would have stopped at 2. I still have pi. I still have 1 over x, the quantity squared dx. So all it does is change that, and thank you for catching that, Andrew, because I just read it as x, because I really liked x, I guess. How was that? How are we doing? A little bit better? Okay, so I'm going to do this last example. Tomorrow when I see you all, we're going to do the washer method. And what the washer method is that we're going to have holes and stuff. So if we have holes and stuff, how do we deal with that? Now, you said, but what, didn't we have holes up here? Well, for this one, we didn't really truly have a hole here at B because I'm still only working with one function. I had a hole, it's a donut shape, but I only was working with one function. This function right here, that, let me do this, that cosine wave really wasn't there. I just used it as a marker to show where my secant wave would have been. So it really was only one. Tomorrow when I see you all, after I finish this example, we're going to talk about what happens when we have to worry about the upper and lower. This is when we're doing a volume and we have the area between curves that we're going to be revolving. So let's just go back to this one really fast. And we're going to be doing the these two graphs. So I'm going to graph both of these so I can kind of get an idea of where they are. My sine wave looks like this. Here's pi. Here's 2 pi. My cosine wave looks like this. So down, and then it comes back up. So here's pi over 2. The place in which they are crossing is right there as pi over 4. At pi over 4, they have the same value. So I want to go from y is equal to sine x to y is equal to cosine x. So I'm going to sandwich it between sine and cosine. And I'm going to have it to x starting at x equals 0. So the shape I am going to be integrating is that shape right there. And this is going to lead us into the washer method. Is my radius at any given time on this is going to be my upper one, which is going to be the cosine. So y2 minus y1. y2 is my upper one, which is going to be the cosine of x. My lower one is going to be the sine of x. So my radius is going to be cosine x minus sine x. So that's going to be my radius. So when I do this integration, I'm going to integrate from 0 to pi over 4 because that's where the two cross. I have pi, and then I have to multiply by my radius, which is the cosine x minus the sine x, the quantity squared dx. Now what I'm going to do on this is I'm going to go ahead and multiply this out. So from 0 to pi over 4 of pi, I'm going to pull that out. And then I'm going to multiply this out. And when I multiply this out, I'm going to get cosine squared x minus 2 sine x cosine x plus sine squared x dx. Now, we're going to get our handout that I sent to you on Pre-Calculus 2 formulas. We know that these two combine, if I have cosine squared x plus sine squared x, this equals to 1. And whenever I see 2 sine x, cosine x, this is equal to the sine of 2x. So this is equal to pi, from 0 to pi over 4, of 1 minus sine 2x dx, which is a much easier solving for integration. So let's just quickly integrate this thing. So this is going to be equal to pi. The integration of 1 is just x. And to have got sine when I did the derivative and a negative sign for that, I must have started out with cosine. And I also has to have a multiplier of 2, but I see the multiplier of 2 missing, so it's going to be plus 1/2 the cosine of 2x, integrated between 0 and pi over 4. And I will let you finish that off. Tomorrow, we're going to pick up more of these. Is there any questions on what I did on that last one using all of my trig functions that we all forgot? Any questions at all? All right, if you have no other questions, then I want you to enjoy this lovely Western Washington rain. Hopefully it'll get a little bit nicer, but you know, rain's okay too. If we didn't like rain, we wouldn't be living on this side of the state. You all have a great afternoon, and I have office hours between 12:30 and 2 today if you need extra support. Otherwise, hopefully you're caught up or getting caught up on your homework. Tomorrow I will put a quiz, a take-home quiz in the Canvas, and if you would like to work in a group, just let me know you'd like to work in a group. You can work in groups up to 3. If you already have people that you want to work with, just let me know. If you don't have people and you want to work in a group, just let me know and I'll find a group for you to do the quiz. You don't have to let me know right away, so you can take a look at the quiz first and then make the decision. So otherwise, have a great day. See you all tomorrow.